Hi, in this video we're going to talk about solubility equilibria, and this is going to involve salts with limited solubility. So a few units ago we learned that some substances are insoluble and some are soluble. For example, everything in group 1 are soluble, and some substances are insoluble like carbonate, phosphates, and ammonium, etc. Let's take a look at calcium Ca3 phosphate PO4 2. In our chart, it says all carbonates and phosphates except group 1 and ammonium are insoluble. So we learned that this is insoluble. But the reality is all substances are to some extent soluble. So what's going to happen is this salt, Ca3PO4 solid, is going to form Ca3Ca2 plus aqueous plus PO4 2PO4 3 minus aqueous. Very small amounts of calcium phosphate will dissolve in water, and it will form Ca2 plus and PO4 3 minus ions. Alright, so far we've learned a lot of K's like KEQ, Ka, Kb, etc. And now we're gonna learn a new one called KSP. And KSP is solubility product. In this particular example, the solubility product is going to be, all K's are essentially products divided by reactants. So KSP for the solubility product for calcium phosphate is going to be Ca2 plus cubed times PO4 3 minus squared. And since both of these are aqueous, that's why we include it. On our right side, which is on the bottom, this is a solid, so there won't be anything in there. So this is just so this is our equation, and we do not include the Ca3PO4 because it's a solid. So there are two ways to express solubility. We have one, which is molar solubility, and this is moles divided by liters, aka molar. And the second one is solubility in grams of solute per liter of solution. Alright, let's first take a look at molar solubility. So in molar solubility, the number of moles of solute in 1 liter of a saturated solution is moles per liter. Concentrations of the ions in the solubility product expression, aka our KSP up there, are also molar concentrations. And KSP can be determined from molar solubilities. So for example, it says if the solubility for FeOH 2 in water is 7.7 times 10 to the negative 6 molar. Alright, this is solubility. At a certain temperature, what is the KSP for that temperature? What is the KSP of FeOH2 at the temperature? And so our first step is always to write the dissociation equation. So we have FeOH2 forming Fe2 plus aqueous plus 2OH minus aqueous. And with this, we can tell us what is the KSP. KSP is equal to the concentration of Fe2 plus times the concentration of OH minus squared. And we do not include this because this is solid. FeOH2 is a solid. Right, now, step 2, we need to calculate the concentrations of the ions in solution from the solubility data. So this, we're told that we have 7.7 times 10 to the negative 6. And this, it says the solubility for this, right? This is a 1-to-1 molar ratio. 1-to-1. Fe and Fe is 1-to-1 molar ratio. But our OH, we have 2 of those. We have 2 OH minus. So let's quickly write this equation again. FeOH2 forming Fe2 plus plus 2OH minus. So Fe2 plus will have our given, our solubility of 7.7 times 10 to the negative 6. And this will be 2 times 7.7 times 10 to the negative 6. Now step 3, we need to substitute the concentrations into this equation. So KSP will be equal to 7.7 times 10 to the negative 6, which is Fe. These two correspond. And then also 1.5 times 10 to the negative 5th squared. This is the concentration for OH. 2 times 7.7 times 10 to the negative 6 is 1.5 times 10 to the negative 5th, by the way. And this corresponds to the OH, which corresponds to here, and then we square that. In the end, we need to square that. Now all that is taken care of, we can just plug into the calculator and solve for the KSP. So if we grab our calculator, 7.7 e to the negative 6 times 1.5 e to the negative 5th squared is going to give us 1.7 times 10 to the negative 15. And that is our KSP for FeOH2. Now we're taking care of molar solubility. Let's take a look at solubility. All right. Our second example. It says the solubility of calcium sulfate is found experimentally to be 0.67 grams per liter. And now we can calculate the KSP with solubility this time. So let's calculate calcium sulfate. CaSO4 solid forms Ca2 plus SO4 2 minus. Both of these are going to be aqueous and aqueous. Now the KSP will be concentration of Ca2 plus times the concentration of SO4 2 minus. Since both of these are 1 to 1 mole, 1 moles to, okay, so both of these only have 1 moles, we won't be having any squares or cubes in our SP equation. Because remember, any K is products to their most power. Since both of these are 1 moles, it's going to be to the first power. And then step 2, after we got the equation, we need to use the solubility and calculate the molar concentration for each ion. So let's see, it told us that it's 0.67 grams per liter. And with this information, we're supposed to calculate the KSP. And what we need to do is first convert this into moles. Grams per 1 liter times, let's see, we need to convert it to moles per liter. All right. So 1 mole has how much? CaSO4 2 minus. Let's go grab our periodic table. Ca is 40.08 plus S is 32.07 SO4 plus 16 times 4 to give you 136.2 grams. And now this is going to end up equaling to, let's see, 0.67 divided by 136.2. It's going to give you 4.9 times 10 to the 1 to third times 10 to the negative third per liter. This is moles per liter. And now we are given molar concentration. So at equilibrium, our concentration of CaSO4 is going to be equal to our concentration of Ca2 plus, which will be equal to our concentration of SO4 2 minus. So these two will be equal to each other, and we're given this much molar solution. So it's going to be concentration of Ca2 plus is equal to concentration of SO4 2 minus. Again, they're 1 to 1 mole ratio. So which is why they're equal to each other, which is equal to 4.9 times 10 to the negative 3 molar. Now we plug this into our KSP equation. So since this is going to go over here and over here, since both of these are equal to each other, that makes our calculation really easy. KSP is going to basically be equal to 4.9 times 10 to the negative third times 4.9 times 10 to the negative third. And this is basically 4.9 e to the negative third squared, which will be KSP equal to 2.4 times 10 to the negative fifth. And that is our KSP for CaSO4 2.